Okay, we are going to pick up where we left off yesterday or on the last lesson. So we're using the same note sheet from 7.3 called the shell method, focusing on still finding the volume of solids of revolution. So as I talked about in the last lesson, today we are going to kind of focus on, well, when are we going to use the shell method versus when is the disk method still going to be the better choice? Okay, so the key idea that I want to remind you is yesterday we realized or learned that cylindrical shell method has representative rectangles that are parallel to the axis of revolution. I'm going to do some typing today. So the representative rectangles are parallel to the axis of revolution. Okay, now on the other hand, the representative rectangles from section 7.2, which was the disk and washer method, remember disks simply don't have a hole in them and washers do have a hole. The representative rectangles are going to be perpendicular to the axis of revolution. Okay, so with that being said, okay, I went ahead and copied all 4 possible cases, and we're going to look at some key aspects. So when we're focusing on that disk and washer method, okay, and we look at the vertical axis of revolution, we notice right away that the rectangle is indeed perpendicular, and I want to stress that when we're rotating about a vertical axis, we are going to be writing our integral in terms of dy. So vertical to me is always y in my mind, and so dy is the variable we are integrating with. This is for disks and washers. Okay, now on the other hand, when we are looking at a vertical axis of revolution, when we're applying the the shell method using parallel representative rectangles, okay, our variable of integration is opposite of the axis that we are revolving the shape around. Okay, so we can notice that again, on the disk and washer method, we are going to look at this variable and know that we are going to look for our limits of integration on that axis. So the limits of integration are going to come from the y-axis. But then on the other hand, in this case, okay, we see that, yes, once again, our limits of integration are going to come from the x-axis. So limits of integration on the x-axis. So we might want to go back and add, that's not going to want to do anything there on the x-axis. So we might want to add y-axis. Okay, so kind of the key thing is that when we are integrating for the shell method and we're rotating around the y-axis, we are going to use x as all of our functions. But then here, when we are rotating around the y-axis, we are going to use dy. Key idea. Okay, and then vice versa, same thing is going to hold true when we're rotating around the horizontal axis of revolution. So when we're looking at the disk and washer method, if we're rotating around a horizontal axis, then we know that we are going to be thinking that the x-axis is going to call for everything to be written in terms of x. When we have the perpendicular rectangle, then we are going to use the same variable that corresponds to our axis of revolution. But when we're looking at the shell method, if we're rotating around anything horizontal, in this case it's the x-axis, we are going to use the opposite of that variable, which would be y. So the shell method, if we're looking at this as our axis of revolution, is going to have a parallel rectangle. So I really like these diagrams. Okay, shell method is based on the surface area of a cylinder. Okay, so we can also remind ourselves surface area of a cylinder. And then the disc and washer method is based on the area of a circle. Actually, we'll put that in purple to keep our color coding going. Of circle. And this was surface area of a cylinder. Okay, so hopefully our minds are going. We're going to do 3 more examples and kind of really think about when are we going to use each method. So on this first example, it says, when is the shell method more preferable? So it says, find the volume of a solid formed by revolving the region bound by the graph y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 about the y-axis. Okay, so I want to draw this picture first. And if I draw my parabola, okay, and we're going around the y-axis, so if this is x equals 1, y equals 1, y equals 2, and this is maybe x equals 1, x equals 2, and I go ahead and plot my vertex, and no, I go out 1, up 1. I see that this is my parabola. And then we are going to look at the area that is bound by y equals 0. So that's right here. X equals 0 and x equals 1. Okay. And the first thing we want to talk about is the disk method as we rotate around the y-axis. So if I'm using the disk method, my rectangle has to be what? Perpendicular. But if I draw in my perpendicular rectangle here, I notice that rectangle has nothing to do with the original function we're basing this off of. If I draw my rectangle here, then I do see that my height of the rectangle is somewhat going to be defined by the function. So this, right away, when I want to use the disk method, I have to use a 2-part integral. I have to use an integral to represent this region, and then a separate integral to represent this region. So I'm going to go ahead and set up my region 1 integral, and I'm going to think about pi r squared because disk method has everything to do with area of a circle. And I'm going to think about, okay, if I'm rotating about the y-axis, then how can I kind of describe the radius of the circle from 0 to 1? So those are my limits of integration right there. Well, it's just simply going to be constant. The big R is, or sorry, just R in general, there's no big R, is going to be 1. But I have to square it. dy. Okay, but then when I hit 1 and I look at the region from 1 to 2, I have to make a new integral because this is where I'm going to have to think about my big R and my little r. This is going back to section 7.2. So I am looking from 1 to 2, and my big R is going to go from the vertical line at x equals 1, right, all the way to the axis of revolution. So my big R is just going to be 1. That's the function x equals 1. But then what is my little r? My little r is going to be defined by the rectangle drawn from the curve back to the axis of revolution. So that is going to be using this function, but I have to rewrite it in terms of x. So I have y equals x squared plus 1. Move my 1 over. Square root, so x equals the square root of y minus 1. So that is my little r. Okay, And when we use disk method, okay, the axis of revolution gives us the variable that we need to write our integral with. Yikes. Okay, so this is a long integral, but we can certainly evaluate it. All right, so if we go ahead and evaluate our integral using our calculator, okay, I am going to kind of jump ahead and say that this entire thing right here, when you do both parts separately and you add them together, you are going to get 3 pi over 2, and you can pause me and try it, which is approximately 4.71. Okay, but this is from 7.2, so I'm not going to focus on all the behind the scenes work. But now we want to do the same problem, but we want to use the shell method. So if I go ahead and, let me circle this real quick. Okay, if I go ahead and draw my axes again, and I think about 1, 2, drawing in my parabola, and then I have, let's see, like 1 here, and I'm looking at going ahead and taking this space and rotating it around the y-axis. If I use the shell method, my representative rectangle has to be parallel to the axis of revolution. Okay, so the height is going to be defined by the original parabola that I have right here. So if I rotate it around, I can kind of picture that cylinder taking shape there. And if I rotate maybe my tall rectangle at the end, I can see my cylinders taking shape. So it's cylinders and cylinders and cylinders. And we are going to use the fact of 2 pi RH, which is the surface area of a cylinder, but we are going to integrate it, and our radii are going to occur all the way out to the value x equals 1, because it gave us those constraints. And our function starts at the axis of revolution. So we're going to go from 0 to 1, looking on the x-axis, and we're thinking about what is the radius defined by? Well, the radius is simply defined by the value of x. But then what is the height of the rectangle defined by? The original function of the parabola written in terms of x. Remember, it's opposite of the axis we're rotating around. So we've written this now in terms of x. And this is definitely a much easier integral to look at and to evaluate. Okay, so we could look at this and know that we have 2 pi times the integral of x cubed plus x dx. Okay, and then we can go ahead and evaluate. So we have 2 pi times 1/4 x to the 4th plus 1/2 x squared, going from 0 to 1. And then we have 2 pi, and it's going to be 1/4 plus 1/2, which is 3/4. But then when we multiply in by 2, we have 6/4, which reduces to 3/2, so we have 3 pi over 2. So yes, once again, you could use your calculator, but I would not be nearly as reliant on that calculator for the shell method as I would be for the washer method. Okay, what was the advantage of the shell method? In this case, it only took one integral in order to find the volume using the shell method. But in the washer method or the disk method, how many integrals did it take? It took 2 separate integrals that were then added together. Sorry, that got a lot of work there. I should probably space it out a little more. Okay, so now in this next example, okay, we just saw that you could have used either method. In a lot of problems, you can use either method, but one is going to be less complex or messy than the other. But on this example 4, okay, it says a pontoon is made by rotating the graph that you see in the picture, 1 minus x squared over 16, from -4 to 4, about the x-axis. So this is our axis of rotation, okay? We want to find the volume of rotating this pontoon. Okay, so you can see in the picture right away that the rectangle that was drawn is what? The rectangle is perpendicular to the axis of revolution. So a lot of times when you start these problems and it doesn't say use this method, you have to find the rectangle that makes the most sense. So in purple, we see that the purple rectangle is perpendicular. That means perpendicular to the axis of revolution. Now in green, I might draw this parallel rectangle. But if we have a parallel rectangle, we should immediately be thinking, how are we going to define the length of that rectangle if it's using the exact same function for the bottom and the top of the rectangle? If you use the same function for one rectangle to define its height, it's going to be a very hard problem. So why do we like the purple rectangle better? We like it because one function is used to define its height, not the same function, if that makes any sense. Okay, so because we have a rectangle perpendicular to the axis of revolution, right away you're thinking we want to use the disc washer approach. So this is the thought process that I would recommend you take before you dive in and just automatically choose one or the other method. So if we're going to use disc and washer, that is section 7.2. So you've got to be able to move back and forth. That's what's going to confuse some of us. So we're thinking area of a circle, pi r squared. So we are going to go from 0 to 4 with our representative rectangles. You can always draw in multiple. Sorry, not 0 to 4, negative 4 to 4. And what is going to define the height of all of those rectangles once I then rotate them around the axis to create that pontoon shape? It's going to be the function written in terms of x, because I got my limits of integration off of the x-axis. So you have to keep that variable consistent. So this would definitely be an integral that we could evaluate because it's just x squared with a 1/16 out front. But that's not the point of this lesson, so we can go ahead and know that if we use our calculator, whoops, what did I forget? Tell me. I forgot the squared there, pi r squared. That's huge. That's a common mistake a lot of us like to make. So when you do this and you use a calculator, remember when you get your decimal approximation disregarding pi, you can still just automatically go to math, enter, and it'll take you to the home screen and give you 64/15 because this one works out nicely. Most of them in the textbook do. So 64 pi over 15 is the exact answer, which gives us approximately 13.40 feet cubed, because I think they said they wanted it measured in feet. Okay, now I kind of already made this reference, but for the purpose of notes, we might want to note that if we used the shell method, then if we look at kind of the same quick picture and draw that arch shape, and we try to define or draw in our parallel rectangle, the big question that you have to ask yourself is, how would we define the height of the rectangle? I don't know. Okay, yeah, you could start by trying to solve for x rather than y, but I don't know that that would necessarily take you to where you want it to be. Okay, so that is a direct comparison of, even though I'm teaching you a new method, sometimes we still want to turn to that original disc and washer method. Okay, the final problem that we're going to do, it says when the shell method is necessary. Let's go ahead and look at the graph and then I'll point out why we can't use the disc and washer method. So it's asking us to find the volume of a solid formed by rotating the region of the graph x cubed plus x plus 1, the line y equals 1, which is horizontal, and x equals 1. About the line x equals 2. Let's see here. Oh, sorry. The line y equals 1 is horizontal and x equals 1. my bad, I just had a little bit of a brain freeze. X equals 1 is right here. So this is the region that we want to focus on rotating, okay? And this is an important question. This is kind of what we struggled with on 7-2. Now we are rotating about an axis that is not the X or Y axis. So please pay close attention to this problem so you know what to do in future problems, okay? Now, you might think, well, certainly we could go ahead and do disk method, okay? Because if we were going to do disk method, you might not want to draw these in right away, or you might want to draw a separate picture. If we were to do disk method, this would be my big R, and this would be my little r, all right? So I have my big R, and I have my little r. But in order to define my big R, okay, I would have to take 2 minus this function, this part right here, which is defined by the original function, but I have to get it written in terms of x. So if I look at my original function and think about trying to solve for x, because I have the x cubed and I have the x, it is going to be very, very difficult and messy, if not impossible, to solve that for x. So that is our barrier. So if we were to use the disk method, we would need to solve y equals x cubed plus x plus 1 for x. This is not easily done. We don't want to mess with that. So don't be the stubborn person that tries to sit there and do it. We have to then turn to the shell method. Okay, so in the shell method, we're still rotating around x equals 2. And we're looking at this region right here. So the shell method is going to use our represented rectangles that are what? They are parallel. So shell is going to use parallel rectangles. So I'm going to go ahead and draw in my rectangle and think about the length of the radius. The radius is always drawn to the axis of revolution and the height of the rectangle. Okay, so this takes extra thinking. So when I look at the radius from my representative rectangle, I'm thinking about how can I describe the length of this blue line? Well, I'm probably going to start at my axis of revolution that is 2 units long, or away from the y-axis. So my radius is going to be greater than or less than 2. Okay, well, it's definitely going to be something less than. But if I think about the full length of 2, what do I need to get rid of on this representative rectangle? I need to get rid of this little chunk right here. I need to erase it off of my line that is 2 units long. So when I say erase, okay, that means I have to subtract. And where am I at right here? I look at the x-axis, so I'm just using x. So 2 minus x is the length of the radius. Now, how do I represent the height of my purple rectangle? Well, we certainly know that it's not going to be defined only by the function, but we start with the function and we think about what do we need to erase off the function? We need to erase this black part right here, which is 1 unit long. So I have to take my function, x cubed plus x plus 1, and I have to erase or subtract 1. You've got to draw the picture and think. Unfortunately, you can't just memorize in this situation. So the hard part is over. We now can go ahead and apply our shell 2 pi RH. So we are going and we're thinking about, then we can draw in multiple rectangles and decide where do we start, where do we stop. Well, that's going to come from the x-axis. So we have 0 to 1. We are going to take our radius, which is 2 minus x, times the height, which is x cubed plus x. And then when I take 1 minus 1, because nothing else is being distributed in, that ends up being 0. and then I'm writing it in terms of x. Thank goodness, because again, we couldn't solve easily to get it written in terms of y. So now from here, we can go ahead and utilize our graphing calculator to evaluate this integral. Press math enter, and you'll get 2 pi times 29 over 30. I encourage you to try to get the exact answer whenever your calculator does convert it to a rational value. And then when we take 2 over 30, that gives us 29 pi over 15, which is approximately equal to 6.07 units cubed. Okay, so this is our answer here. All right, so no, I don't expect you to be a master after just seeing one example of this, but the next few days, kind of looking at what happens when we rotate on an axis that is not the X or Y axis is going to be something we want to try to come closer to mastering, okay? Keep working hard, keep asking me questions, you're doing great, and let's keep working at mastering shell, and then also knowing kind of when to use disk and when to use the shell method.